All right, so again, we got to compute the limit of the sequence or show divergence here. So if we begin with part A states that we have the limit as k approaches infinity of k to the third over 4e to the k. So if I were to just use, let's say, a direct substitution here, you would have noticed that you would have got infinity over infinity. So what does the infinity over infinity suggest? Do anybody remember from class?
Hopital's rule.
That's right. So this would imply that you can use your L'Hopital's rule. So remember, L'Hopital's rule says that anytime you have an indeterminate form, you can take the derivative of the numerator and denominator until you can get to a point where you can evaluate the limit, right? So by applying L'Hopital's rule, we're going to have the limit as k approaches infinity of 3k squared over 4e to the k, right? The derivative of k cubed is 3k squared. Derivative of 4e to the k is just 4e to the k. Now, notice that as k goes to infinity, we have to use L'Hopital's again, right? So L'Hopital again. We're going to get the limit as k approaches infinity of 6k over 4e to the k again. But, just looking at this is going to give you infinity over infinity. So use L'Hopital's again. Now, if I use L'Hopital again, we have the limit as k approaches infinity of 6 over 4e to the k. If you evaluate this limit now, this will basically say that you have 6 over infinity. And 6 over infinity would represent a really small number, so this limit would go to 0. And that would be the solution to part A. So this was a case where you had to use L'Hopital rule a couple of times, at least 3 times here. Let's try to look at part B together. So for part B, it states that we have the limit as k approaches infinity of sine cube k over k. How do you think we're going to solve this? Yep, there you go, Alvin. You said it in the chat. We're going to use the squeeze theorem. Why can I use the squeeze theorem? What do I know about this? What do you know about as k approaches infinity? What do you know about, let's say, sine of k?
The altitude is between 1 and -1.
Yeah, that's right, Preston. So we can make a quick note. We can say that your sine of k by itself, it's bounded between -1 to +1 as k goes to infinity. So what I'm going to do is rewrite this this inequality so that way the middle part could mimic the sequence, right? So observe, we have -1 is less than or equal to sine of k, which is less than or equal to 1. Now notice that our sine of k here in the sequence is raised to the third power. So I'm raising -1, sine of k, and 1. All of them is being raised to your third power here. So if I raise all of them to the third power, -1 to the third power is just -1. Sine k to the third is just sine to the third of k less than or equal to 1 to the third, which is 1. Now, the only thing that's missing, so that way this middle piece of this inequality can mimic our sequence, is the division of k. So what I need to now do is divide everything by k. All right, so this gives us -1 divided by k is less than or equal to sine cube of k over k less than or equal to 1 over k. So the way that the squeeze theorem works is that, okay, we show that the sine cube of k over k is bounded between -1 to the k and +1 to the k. So you want to compute the limit as k approaches infinity of your left and right endpoints, basically. Right? So we take the limit as k approaches infinity of -1 to the k. Well, what do we know about this limit? What would it equal to? As k goes to infinity. -1
0.
is going to be 0. And the limit as k goes to infinity of 1 over k is also 0. So lastly, I'm just going to write it underneath here. Thus, by the squeeze theorem, I'm going to abbreviate it as SQ, or I can spell it out, it's fine. By the squeeze theorem, we have that the limit as k approaches infinity of sine cubed k over k is also equal to 0. And that's a solution to part B, right? So part A, you had to use a L'Hopital's rule. Part B, you saw that you can use a squeeze theorem. For part C, I'm going to write it out. We have the limit as k approaches infinity of 7 over 3 to the k. Anybody know what I'm going to use, what method for part C?
It's a geometric series.
That's
So,
right. Basically,
yeah.
it's a geometric. So we're going to mimic it to look like a geometric. First thing is, you can always pull your constant multiple out. You can pull the 7 out. So we get 7 times the limit as k approaches infinity of 1 over 3 to the k. You should be able to recognize what your r is, because technically speaking, if I said I had 1 to the k here, right? 1 raised to any power is always what?
Itself.
Itself is going to be 1. So what we're going to have is 7 times the limit as k approaches infinity of 1 over 3 to the k power. So you should recognize that the 7 is my a, 1/3 is my r, right? So if r is equal to 1/3, then what do we know?
You use the formula a over like 1 minus r.
Right, so because r is equal to 1/3, we know that it's geometric, it converges. And it converges to the sum a over 1 minus r. Right? So to figure out what's your a and what's your r, you just look at what I have written. We have 7 over 1 minus 1/3. Well, 1 minus 1/3 is 2/3. So this is 7 over 2 divided by 3. You could flip 2/3 as 3/2 and multiply it by 7. So this gives us 7 times 3/2, which would be 21 over 2. And that would be the solution to part C.